Okay, so very happy to have Denis Nesterov from University of Vienna giving us a series of 3 talks. So the first talk title is going to be Quasimaps to moduli space of sheaves.
Exactly. Yeah, thank you very much. Yeah, I first want to thank Andre and Nina for inviting me here and giving an opportunity to speak. And it's also my first time in the United States, and it's been just wonderful. So thank you very much. And yeah, so there will be 3 talks. Let me briefly go through the plan then. So the first talk, today's talk, is titled Quasimaps to moduli spaces of sheaves. So I'll define what it is and discuss some basics of this Quasimaps to moduli space of sheaves. And then the first talk will be the theoretical heart of it. So it's the wall crossing. So the wall crossing between the Quasimap invariants and the Gromov-Witten invariant. Wall crossing. This wall crossing is governed by an I function, or in other language it's also called vertex. And I'll talk about applications of this wall crossing. So together, these 2 talks, so there is a pictorial representation for the content of these 2 talks. So these 2 talks will give us an equivalence between so-called Donaldson-Thomas theory of a surface times a curve with a Gromov-Witten theory of some moduli spaces of sheaves M on a surface S. So I'll denote MS. To be more specific, that will be an equivalence between so-called relative Donaldson-Thomas theory and the Gromov-Witten theory of MS, of a moduli space of sheaves on the surface. And this equivalence, so what it is, it will be some kind of a change of variables formula, which is governed, which is like given by this vertex. And if you don't know what it means, I'll define everything. So vertex. So this is the content of this first 2 talks, and the third talk, it will be called enumerative mirror symmetry for modular spaces of Higgs bundles. On a curve. And so what will this be about? So I'll just drop some names here, some terminology, and then in the third talk I'll explain what these words actually mean. So it will be following duality. So it will be a statement that will relate so-called Vafa-Witten invariants to Quasimap invariants, and this can be represented pictorially as follows. So Vafa-Witten theory of a curve times another curve, C times C prime. So this will be related to SUR Vafa-Witten theory will be related to P SUR Vafa-Witten theory. By so-called S duality. So this is enumerative S duality. And the Vafa-Witten theory, in turn, will be equivalent will be shown to be equivalent to Quasimap theory. And this will be called Vafa-Witten Quasimap correspondence. Quasimap theory of moduli spaces of Higgs bundles. Quasimap theory of moduli of Higgs bundles. So Quasimap theory of moduli space of SUR Higgs bundles, and down here you will also have the same related relation between Quasimaps and Vafa-Witten theory of moduli space of P SUR Higgs bundles. So I'll explain what it all means in the third talk, but it just so that you have a pictorial representation of what will be happening. And so this S duality on this side will produce a certain duality on this side, which we'll call enumerative mirror symmetry. And will relate curve counting invariance of moduli spaces of SUR Higgs bundles to the curve counting invariance of moduli spaces of PSUR Higgs bundles. And so this is the content of the third talk. And let me just finish the plan with the following. I mean, for those who are interested, I can discuss in a private conversation about. So you can actually complete this picture also to the square, and the square looks like this. So you have a Donaldson-Thomas theory of a surface times a curve. But you also can consider Gromov-Witten theory. Of surface times a curve, relative Gromov-Witten theory. So these two are related by so-called Donaldson-Thomas Gromov-Witten correspondence or MNOP correspondence. And then on this side, so you have also relation between Gromov-Witten theory of S times a curve with a Gromov-Witten theory of the orbifold symmetric product. And so on this side, where the moduli space of sheaves is taken to be a Hilbert scheme of endpoints, you have a so-called Kreppmann resolution conjecture that relates the Gromov-Witten theory of Hilbert scheme of endpoints to the Gromov-Witten theory of the orbifold symmetric product. So orbifold symmetric product is just you take the surface and copies of the surface and you quotient by the symmetric. And so these two, so if MS is just the Hilbert scheme, this is a Kreppmann resolution conjecture proposed by Rohan. So, but I might squeeze it in a second talk, and we'll see how much time I'll have. And if I don't have time for that, I can tell interested people in a private conversation about that. So that's roughly the plan of the talk, of the three talks. And so we'll start with a Quasimaps to moduli space of sheaves. And so how does it work? Go up. Do you have any questions about the plan?
So the vertical arrows are written. So
here?
Yeah.
So it's in this case it's just really inequality. So I mean, as I said, yeah, I should have specified that over here. So Donaldson-Thomas theory on the S times a curve is really equal to the Quasimap theory. So this correspondence is just this correspondence is provided by identification of moduli spaces, but I'll talk about it. So it's really, so this, let me write it here. So this is really equal to Quasimap theory of MS. So there is a really equality in the sense that the moduli spaces are isomorphic and the corresponding perfect abstraction theories are isomorphic. And this is just essentially this equality. So Vapo-Witten equal to Quasimaps. Oh, there is something to, I mean, it's not really only that. You have to kind of relate the classes on one side to classes on the other. So you have to relate chain characters of sheaves to the degrees of Quasimaps and so on and so forth. But yeah, so this is just a plan. I will talk about it more specifically in the third talk. So let me start with the Quasimaps. Yes. So if you take C2, let's say, or it depends. So if you take Hilbert scheme of endpoints of n surface, it depends on, you can embed it in many stacks. You can embed it in the stacks of all sheaves. You can embed it in the perverse sheaves. You can embed it, I mean, and that how perverse it is, you can also change, right? So you can tilt with respect to the zero-dimensional sheaves. You can tilt with respect to one-dimensional sheaves. And so I think tilting with respect to one-dimensional sheaves will actually give them the Q variety, and then it will be equivalence between Brine-Steinberg pairs and Quasimaps to the stack given by the Q variety.
Right. So this is this Quasimap equivalent, and this is
Yeah.
And then are you saying that there will be equivalence of that, equivalence of that with, you know, whatever, anything, any of the equivalent, like whatever, Hilbert scheme of threefold or pairs,
so you're saying that whether I can prove, let's say, PTDT or Brine-Steinberg DT?
Yes.
With that you also can, yeah, you can, I mean, in some circumstances you can do that. Yeah, you can express a relative PTDT via this Quasimap wall crossing. You go first to Hill, and then you tilt the heart, and you go to different Quasimaps, and then it gives you. I'll talk about it if I have time.
In what?
I mean, it also works in K theory. I mean, there is quite a K theoretic wall crossing, but I haven't. I mean, there is in a JT situation, there is a K theoretic wall crossing.
Okay.
And it should. I mean, if there is something in JT, there is something in this setup as well. But I haven't. I mean, I don't know much about K theoretical version of it.
The double hour equal signs are cars of mappings, and the others are equivalents.
Sorry. So you're referring to the fact that so both. I mean, I just all of that is just. Sorry, I just didn't. Yeah. Sorry. It wasn't deliberate. It wasn't deliberate. Yeah. And the arrows are there as well. So okay. So let me start now with the part one. So Quasimaps to model space of sheaves. So the setup, so the chapter will be called Gromov growth and Grothending. And so okay, so what is our setup? So S will be some smooth quasi-projective. I mean, if you assume that it's quasi-projective, not projective, you have to also assume that there exists a nice torus action, projective surface. over complex numbers. And C will be, for the moment, just a smooth curve over complex numbers. So what we can consider a basic moduli space, just it's called MCS for this moduli space. So it just maps from your smooth curve C to your surface S. And the speaker last week said that studying non-proper spaces is like doing chemistry with a flask that has a hole on the bottom. So the same applies to this moduli space. So this moduli space is not proper. Well, you can take, for example, we'll discuss this example in detail. You'll take just elliptical curves mapping P2 in degree 3. So how can you compactify? Well, you have two choices in this situation, I mean, among others, but two that will be of interest for us. So the first compactification comes from the Gromov compactness theorem. And what is this compactification? This is called MC bar of S. And this is, so you consider maps not from the curve C, but from the bubbling of C. I'll show you in a moment what it is. So from a bubbling of C, you now consider maps through S. So what is this bubbling? So what is the boundary? What did we add? So what is the boundary? So what we now, instead of considering maps from our curve C, we allow this curve C to attain these rational tails. So it's P1 components attached transversely to C. And you consider maps from these configurations too. So this is the fact that this moduli space is compact is provided by Gromov compactness theorem, and this is beginning of Gromov-Witten theory. So Gromov-Witten theory studies maps from configurations of curves like that. So another compactification is provided by Grothendieck, namely by his theory of Hilbert schemes. And so what is the compactification? This is a Hilbert scheme of one-dimensional subschemes on S times C. How do you embed maps to this Hilbert scheme? Well, you just take a map. You take a map, and a map is determined by its graph. So what is a graph? A graph is just a variety in S times C. So you send F, your map F, to corresponding graph. And but then of course you take this Hilbert scheme of one-dimensional subschemes that has things that are not graphs, right? And I'll show you in a moment how they look like. So one refers to the fact that your graph must be of degree 1 over C. So what did we add here? So let us consider the boundary that we add. How does it look like? So you have our S times C. Here you have a graph of some map. But now this map, so this graph might degenerate, and so it might attain some vertical component or some floating point. And so this subscheme, so by that I mean some one-dimensional subscheme that completely lies over some point in the curve. And so this one-dimensional subscheme is no longer a graph, right? So this Hilbert scheme of one-dimensional subschemes will contain something that are no longer graphs. So this is the two compactifications. Let me just say that the Gromov compactness theorem holds in a symplectic category, while this is just purely algebraic. I mean, you have Hilbert schemes for not only for projective varieties, but the properness of these Hilbert schemes uses in essential way uses the fact that you can embed your variety into the projective space. Okay, so let me just show you how these compactifications are, also in what way they are different. And so let's consider now an example. So you have an example simple. So you have your elliptic curve mapping to P2. So what is the equations of elliptic curve in P2? Just that, up to change of coordinates. And assume that these coefficients that are dependent on some parameter t, they tend to 0. Okay. So what happens in the limit when they tend to 0? And there are, well, you can take three limits depending on what moduli spaces you consider. If you consider just embedded curves, so just polynomial equations of degree 3 in P2, so the limit will be just a cusp. It will be a curve defined by the equation x squared equals 3. So it will be just a cusp. So this y squared, sorry, plus 3, and this looks like that. So this is supposed to be the cusp. So this is just the limit in terms of the polynomial equations. What is the limit in terms of the Gromov-Witten theory? So, or the not Gromov-Witten theory. So this moduli space. So the limit in terms of this moduli space will look like that. So you have your elliptic curve being embedded into P2, and then well, elliptic curve cannot map to the cusp, so something must happen to the source of this map. So to the elliptic curve itself. So in fact, it will attain. So this is our elliptic curve, and it will attain this P1 bubble that maps now to this cusp, and it's mapped to the cusp at exactly the intersection between this P1 and E, and the map is just a 1-to-1 over here. So this is a map. So this is a map from a configuration of the curves like that to P2, right? So this lies all in P2. And so what is the state? What is the limit over here in the case of a Hilbert scheme? Well, limit in the Hilbert schemes. So you just look at that. So your elliptic curve cannot map to the cusp. So it the corresponding graph must degenerate in some sense, in some way. And so how does it degenerate? So you have now a copy of your elliptic curve lying completely horizontally. That refers to the fact that this elliptic curve over here just contracted. So this is contraction over here to the cusp. Contraction. And so this just refers to the fact that your elliptic curve just contracted to the point in P2. And then here you have a completely horizontal cusp. So this is exactly the equation. Lying completely vertically in P2. So this is examples of how these compactifications are different. Do you have questions? Yeah.
So what would be the family of graphs as uniform T that would limit that on
Yeah, so it will be like, the family of graphs just will look like that. I mean, it will be just graphs of the embeddings of this elliptic curve into, I mean, I don't know how more precise it can be. It will be graphs corresponding to embeddings of P2 to E. Oh, sorry, of E to P2 to P2. And then in the limit, when your embeddings, well, the image of your embeddings become cast, you degenerate your graph in the configuration like, yeah, stuff like that. Okay, so okay, that's just some basics. So it seems like these two complexifications, so the Hilbert scheme and the bubbling of C, they're not very much related. But in fact, if you change your perspective a little bit, they're almost the same thing. So that's kind of. We have. It doesn't erase it. So. You can use that, but is it legal? But it's not supposed to be used like that, right?
It works.
Amazing. Okay. Interesting. Okay, so it seems like these complexifications are not related, but in fact they are related. And this leads us to the topic of Quasimaps to S. Okay. So what is that? For that, we have to define a different space called curly S. So what is this space? The space are sheaves on S, such that the chain character of the sheaves is equal to 1, 0, -1, and the determinant of the sheaves is fixed. Okay. So that's surface.
Oh.
Yeah, that's surface. So how does this space look like? So firstly, S embeds nicely into this. So I have to be careful with curly S and with a straight S. So it embeds nicely into this curly S. And so what you do is you send your point P to the ideal sheaf of P. And that ideal sheaf of a point on S has exactly that chain character. That's why we picked that chain character. So I want to say that the chain character is that. So there are other two types of points. So one of them is given like that by the following sheaf. You take a structure sheaf of a point, P1, P1, yes, and the disjoint union with a P2, and then you take a direct sum with an ideal sheaf of P2. And you can check by additivity of chain characters that this also has the same chain character, 1, 0, -1. And of course, you also have a non-trivial, I mean, you have an equivalent, you might have an equivalent non-trivial extensions of such kind. And the third type of points, well, you take some the one-dimensional subscheme gamma. You take a disjoint union of gamma with P2 with another point, so and then you take an ideal sheaf of gamma now, where gamma is one dimension. So this will be like, these points will be complement, lie in a complement of curly S minus S. And so in particular, you can see that, so it's a bit strange, right? I mean, it's difficult to visualize what's happening because it's a very big space, it's non-separated, and it's also of like infinite dimensional. So it can be filtered by finite dimensional substacks, but it's on its own is hugely infinite dimensional. So in particular, whenever you're on a surface, this I mean the fact that you have this kind of points in that curly S imply that this curly S is not of finite type. For those who are familiar, you can think about it in terms of Nakajima-Koiwa varieties as well. You can take the stack on corresponding to the Nakajima-Koiwa variety associated with quiver with one loop, and this will be the stack 1n, and this is in some sense is a similar stack but for arbitrary surface. So this is almost, I will talk about later. It's almost equal to that stack curly, but for C2. Yeah. For S equal. In fact, there are ways of getting rid of this kind of points. So this is the stack. It's huge, like infinite dimensional, very complicated to comprehend what's going on. But how do we define it? In algebraic geometry, in order to define a space, you just need to specify what are your maps, right? From some base scheme B to your space. And so in this case, by definition, your maps from B to this curly S are just given by sheaves on S times B, such that the determinant, sorry, F is flat firstly over B, but then also the chain character. First, the determinant is trivial, and also the fibers, the chain characters of the fibers is just equal to 1, 0, minus 1. So this is essentially definition of this stack. So that's enough to define space in algebraic geometry. So you specify what are maps from some arbitrary base scheme B to your stack. In this case, the schemes are given. Sorry, the maps are given by sheaves on S times B, which are flat over B. Determinant is trivial, and the chain characters of the fibers, so over B, are equal to 1, 0, minus 1. So every sheaf, so because it's flat, it's perfect. You can resolve it by, so every sheaf can be flat over some base B, can be resolved by B, by some vector bundles, finite kind of. So every sheaf flat over B can be can fit into the long exact sequence like that, and yeah, and so you define the determinant of F by just determinants of these vector bundles. So this is vector bundle. You take the alternating determinants of the vector bundles. No, but it might be, if it's not flat, it might be actually not perfect, so it had infinite dimensional resolution. Yeah, so that's why you need flatness. So, and then if you have infinite dimensional thing, you cannot define like tensor products of infinitely many line bundles. So not infinite dimensional. If you have infinitely many terms in this resolution, you cannot define the tensor products of infinitely many lines. Okay, and so this. Yeah, but if it's not flat, it might not be in a K-theory of perfect. Exactly. So okay, so this is the definition of the space. So why did I introduce this space at all? So let's consider actually, well, we consider maps from curves to S. Let's consider maps from curves to S curly. So now take map from curly, maps from C to curly S. So now we consider maps from C to curly S. And so what we require that this map generically it factors through S sitting inside the S curly S. So you see, there is a canonical embedding of S to curly S. So I now say, let's consider maps from C to curly S that generically it lies in a straight S. So, but here, you see, by this definition of this moduli space S curly, what is a map from C to S curly? Well, it's exactly given by a sheaf on S times C, which is flat over C. But since C is the curve being flat, and over C is equivalent to being torsion free as long as you're generically torsion free. So we said that generically it maps to S. So since F is an ideal sheaf for generic little c inside bigger C, it means that generically it's also torsion free. And the torsion free on a curve, the generically torsion free on a curve, and flat is equivalent to being just torsion free on a S times C. So in fact, so this is the map from C to curly S is given by a sheaf on S times C, which is so F is torsion free. Torsion free. The determinant of F is a trio, and it's of rank. I mean, it's chain character is of given rank, it's of given type over any point C. So in particular, it's of rank 1. So, but it's a kind of known fact in algebraic geometry. So these sheaves are just given by so torsion free trivial determinant, and of rank 1 is sheaves on the threefolds are given by ideal sheaves of one-dimensional subscripts in this case. So in particular, this implies all of these facts implies that F is just an ideal sheaf for one. So for ideal sheaf for some one-dimensional subsystem in S times C. And this is again, it's a bit of a tautology. I mean, it might seem kind of complicated, but it's really tautological in the sense that that's how you define this moduli space S, and as a consequence, that's what your maps to this moduli space curly S are. So they're really given by sheaves, which are ideal sheaves of curves on S times C, as long as you have mapped generically to this straight S. So what we have shown is that if we consider this moduli space of maps from C to S like that. So this is just a moduli space of maps to curly S generically mapping straight S. So what we've shown, this moduli space is just equal to the Hilbert schemes of S times the curve. So this is definition. This is just not equality, but isomorphism, canonical isomorphism. And so what are these maps? This is exactly the maps to this curly S that generically map to C. Sorry. There is so generically mapping to S. I always mix up C with S. Sorry. Generically mapping to straight S. This is exactly the definition of. This is really just definition of Quasimaps to S. Okay, so let me just pictorially represent it again. Do you have questions? Yeah.
So what does generically mean?
Yes, if you take an open subset of C, then this open dense subset of C lies inside straight S. Yeah. Oh, let's do that. So let me just stress it. So we have these Quasimaps. So Quasimaps are just maps mapping to the curly S that are generically land in straight S. So and this is the most important thing you should take away from the talk. So let me just stress it. So this guy is equal to isomorphic. So how does it look like? Let me write it. So you have let me draw it. I mean, let our curve C. It maps this huge infinite dimensional S. Inside you have our straight S. And how does it map? So it maps almost entirely. It lies inside this straight S, but some points are allowed to go outside of the straight S. And these points will be base points. They will be called base points. And so how does it correspond to the Hilbert scheme? So on the Hilbert scheme side, you have S times C. And this you have the generically. So generically lying in the straight S will mean that generically you have this graph of some map, but then at some points, so this is B1, B2, points B1 and B2. Over some points, you have these components of a curve that will not make the curve graph of some map. And so what are these points? Well, these points are exactly, so let me call this star and star, and this is this star. So these points just correspond to, so star is this kind of a point, and star is that kind of a point. Or some non-trivial extensions, equivalent extensions of that. I mean, non-trivial extensions of this type. So these points, so this points is exactly, so B1, B2 maps over here, and this is the points in this huge curly S that are of that type. Okay. And do you have questions? Is it understandable? Huh?
It's the straight S that open dense subset.
Yeah, exactly. It's actually also closed. But since you're not separated, closed is of no value. Yeah. Okay.
The straight S, the wide is dense.
Sorry, yeah, it's not dense. It's open. Yeah. Yeah. I think actually, if we can, it can. It is dense in some sense. Actually, you can special. I think not in most of the ideal sheaves, you can specialize to arbitrary torsion, like non-torsion free sheaf with that chunk character. No, probably not every, but most of them for sure. I mean that gives you a specialization of an ideal sheaf to some non-torsion free sheaf. So in particular, it means that in some, I mean, you can take a limit of a ideal sheaf to some. You can go as far as you want into the unstable strata of this curly S. It doesn't matter. I mean, it's not important anyway. So okay, analogously, if you can now define this S. So what is this? Is it's just sheaves on S with so sheaves on S, such that the determinant of the sheaves is trivial, and the churn character of the sheaves is equal now 1, 0, minus n. So inside you have just Hilbert scheme of endpoints. Okay, endpoints. So you can consider also Quasimaps now. So maps from C to this curly Sn, such as generically the map to the Hilbert scheme. So this is Quasimaps from C to Hilbert scheme. Oh, how they right. Then this will be the Hilb n of S and C. How does it look like now? So how does it look like? Let me just on this n. This n will now correspond to the fact that you have kind of n many of these horizontal curves, or they can be thickened, but roughly speaking, n many of these horizontal curves, counting also their thickness, counting how non-reduced each of them are. Okay. And so again, this is isomorphism, canonical isomorphism, almost tautologically by the definition of this moduli space of sheaves on S. So, which one? Yeah, you mean how they define this thing?
Yes.
Yeah, just exactly the same, but with a minus n over there. The Chen characters, the Chen characters of minus n. Yeah. Right. Yeah, yes. Yeah, here this. Yeah, so this is C mapping to this stack, generically factoring through the Hilbert scheme endpoints lying inside this this stack. Sorry. So yeah, this is by definition. Sorry, this is just by definition maps from C to this curly n, generically mapping to the straight Sn. That's all. That's everything. That's the only defining property. Mapping to, sorry. Is okay. well, you define it as a stack. You define it just well, you define it as a by a family of maps from so the if you evaluate now, evaluate to some base scheme. This is given from this is given by maps from C times B to this curly N, such that FB, when you take a fiber over any geometric point in B, is a Quasimap. And then you can show that this is a. Then you can show that this as a stack, as a moduli problem. This is isomorphic to the moduli problem of sheaves on S times C. And so the schematic structure is exactly given by the schematic structure that comes from the moduli problem of sheaves on S times C. Okay. So this is all about sheaves to S. Let's now move on to the sheaves to arbitrary moduli space of sheaves on S. Sorry, this is Quasimaps. Let's move on to Quasimaps to arbitrary moduli space of sheaves on S. Unless you have some questions. Yeah. This is just for introduction. I'm gonna vary now the curve. I'm gonna go now to the fullest possible generality. You can vary the curve, yeah. It holds exactly the same story holds. The problem is with the deformation theory. I mean, I haven't mentioned that deformation theory at all, but the same also holds for arbitrary dimensional X. Yeah, you don't have nice deformation theory. Yeah, exactly. I mean, there is a chance that you can get a nice abstraction theory in the case of a S being a threefold. And there was someone is doing that. Someone is studying. I don't know the names, but I know there was a talk on that. I think in Japan. So someone is studying Quasimaps to quiver with the potential, and then they show that these Quasimaps are given by some four-dimensional DT theory on some fourfold. So there is a chance that actually it can work for three-dimensional. Probably, I don't know. Yeah. Okay, so now chapter 3. I think it's chapter 3. Yes, moduli spaces. So how is it called? Quasimaps. Quasimaps in general now. So I have to introduce some preliminary notions. So we'll consider algebraic part of cohomology on S. So this is just by definition. I know that's with the pairing. What is it? By definition, this algebraic part is just Q plus neuron Savary plus Q. So neuron Savary is just, for those who don't know, this is just a lattice generated by proper curve classes. Algebraic curves generated by the class of algebraic curves. And this pairing is just it's a modification of usual pairing. This is Mukai pairing, and it's given by you twist everything by the third class. it's not of big importance, it's just a convention. So we'll need that for some definitions. And now pick some class here. Let's be. And then ample line bundle. And so we'll consider now moduli spaces, moduli stacks of sheaves. These sheaves of this, the chain character now equal to V, and the determinant is fixed. So determinant choice of determinant is redundant in the sense that any choice gives isomorphic moduli spaces or moduli stacks, and now not specified in notation. Sorry, I taken chain character.
Oh, okay.
Chain characters are fractions, but yeah, I can take chain classes. Yeah. So. So inside here, well, yes, sure. I mean, I make some assumptions now. Well, I make some assumption that it's not empty. Actually, well, inside here, you have straight MD, and this will be stable locus. Sorry, a Giesecke stable locus. Stable sheaves.
What is that?
Huh?
What is it?
Some line bundle L. I said it's the isomorphism class of the stack doesn't depend on the choice of L. So I can pick one and then we say if you want to pick another. Yeah. So this is Giesecke stable sheaves. So this is, I mean, for those who know, this is some. Okay, let me first make an assumption section. So this pairs, this moduli space will be subject to the following assumptions. So the first one is that it's not empty. So that Andre is not worried about the fact that V gives you empty stuff. And then the second assumption is that semi-stable is equal to stable, and this in particular implies that MV is projected to the right. And the third assumption is that there exists a universal family. It's not necessary, but it's necessary for simplicity. I mean, it simplifies the exposition. So there exists a universal family. If you don't require existence of a universal family, you have to work with the orbifold instead, and then you have to consider orbifold Quasimap theory, and it becomes just complicated. So you just require that there exists a universal family, and this, in fact, almost equivalent. And if not equivalent, it's the only way to actually show that there exists a universal family. Is that, so this is almost equivalent, let's say, to existence of a class U in a K theory, such that it pairs with V to 1. Okay. And then so this is a huge, again, enormous stack, at least the curly M. And so we want to study maps to this stack, but before actually studying maps to this stack, we have to understand what are the curve classes at all here. And I don't know if it's actually possible to understand what is the cohomology of the stack of all sheaves. Probably it is, but in any case, we'll consider some canonically defined nice curve classes, or dually the divisor classes on this stack, and this is determined line bundle classes. So there exists a map lambda from HV to the H2 of this stack. So what is HV? This is just classes that pairs 0 with V orthogonal to. And what is a map? So what is a map? So it's you send A. You pull back. I'll write now. And let me write it, and I'll specify what I mean by that. You pull back. So you pull back a class, you tender with this chain character of universal sheaf and dot class, and then you push forward everything to the moduli space, and then you take the first degree, so the degree 2 component of this thing. So C1. So how does it look like? So you have your S, you have your curly M, you have your S here, you have curly and here. So this is the first projection. This is the second projection. And here you have the universal family sitting on top. So the reason I take the orthogonal to V is because taking the whole thing will not give you more. So it's in fact this is an embedding, at least yeah, it should be an embedding, but it's not important for purposes of the talk. But so this is the nicest map you can get from the classes on S to classes on MV. I mean, there are some others, of course, but this is one way. So one of the ways to construct classes on moduli space of sheaves. So, and we'll and so we'll take the image of this map to be kind of, we'll define the image of this map to be H2 of M curly. So for example, you can so assume example. So assume that your MV is just this curly S, and so the straight MV is just S. Hilbert scheme of endpoints on S. And so you can pull back now. You can pull back the classes. You can pull back the classes from the curly to straight by the inclusion. So this is inclusion iota. And so the statement is that, for example, if you don't have any Picard, if the the Jacobian of S is trivial, if the Picard is discrete, then this pullback is an isomorphism. So you can view, so it's this determined line bundle construction gives you all classes on a stable locus. You can view this H lambda 2 on curly M as an extension of all classes from straight M, straight M, yeah, to the entire stack. Okay. So this was necessary because I mean we want to study curves, maps from curves to your stack, but I mean the stack is massive, right? So you have to get some kind of understanding what the possible algebraic classes you can have on this stack. There are more probably, but this is essentially the only class that we need for nice definitions. Okay. Okay. Now comes the definition of Quasimaps in general. So a map from a arc curve to your curly B is a Quasimap of degree beta, where beta lies in a dual of this H lambda. So you just, I mean, to define a curve class, you can just take the dual of a divisor class. And so it's a Quasimap of this degree if firstly this guy is just a marked nodal curve. Do you have any questions regarding the definition of a class, actually? No. Okay, so it's this CPI is a marked nodal curve. And then the second is that F generically maps to stable locus sitting inside the curly. And generically again, by generically I mean that the open dense. So in this case, because your curve might be, so it might be non-irreducible. So you require open dense subset maps to the the stable locus. So on every open subset on every component. And so then you require, well, before we considered maps from smooth curves. In this case, we have a nodal curve with a marking, so you have extra points in the definition. So you require that the nodes and markings always lie in the stable locus. And the degree. So we say that it's of degree beta if when you pull back some class from this H2 lambda, let's call this class just some L, then so you pull back a class by this Quasimap, and this should be equal to the applying this beta to L. I'll take degree here. Okay. So this is definition of a Quasimap. Let me just say now what is a stable Quasimap. Oh.
It's like a sheep on the table.
Yeah.
You should say that the utility class of that sheep is like.
But, yeah, but then the curve degenerates, right? So you have to specify, you have to identify in some way the K theory of all degenerations. It's, I mean, it becomes subtle. in the end, it's what you're saying almost, but I mean, that's the correct idea, but to make it precise, you have to do that, but I just wrote that. Yeah, in the end, this class becomes just equivalent. It's equivalent to some Chen character data on threefold. Yeah, that's exactly also why I defined it this way. So it's essentially because it just works. Yeah, so but it's not clear why. I mean, yeah. Well, I mean, but I don't know. It's just you have. I mean, it's an infinite dimensional stack, so you want just some finitely many classes that you kind of can understand, and so that's the way to produce these finitely many classes, and then you evaluate your degree just on those classes. You know, in the end, yeah. So in the end, yeah, and
the class of that sheet.
Yeah, I'll talk exactly. I'll talk. Yeah, exactly. Yeah, exactly. On a fixed curve. Yeah. So let me just write it. So I wanted to actually talk about it in more detail a bit later, but let me just write it now. So degree of Quasimap is literally for smooth. For smooth C is equal to the instance of the Chern part. So yeah, I mean, also in this case, so the Quasimap is given by. Yeah. Yeah, exactly. That's yeah. I mean, that's. Yeah. No, I mean, what you can do the following, right? You can, I mean, yes, and then it's what you're saying. So you can just take the curve. You can consider each of its components, and then it gives a Chen character, and then you can like sum all of them together. Yeah. So, I'll talk about it. So yeah, let me just say before I move on then. So every Quasimap, really, also in this case, I will specify more specifically what is meant here. But every Quasimap, just by construction, again, by the construction of these moduli spaces, is given by some sheaf on S times C. And you can actually say some more about this sheaf. Now I'll talk about it. So what did I want to erase? I want to erase that. Okay. So, and let me finish the definition. So we say that F is stable. It's stable if there are two points here. So as usual, we define that automorphisms of F, there are found many of them. And then the second one, we require that this CPI doesn't have rational tails. And this is the point of Quasimaps, that it allows. I'll draw the picture. So let me just say it doesn't have rational tails. In the theory of curves, this is called that also semi-stable. This is a semi-stable curve. The semi-stable curve is a curve that doesn't have rational. So what is a rational tail? No, so no, it doesn't have only rational tail is a P1 with a special component. So you don't allow any. So then there is no stable Quasimaps. Well, you can define. Yeah, I mean it's just a. What you're thinking about is usually in the Quasimap theory is called the graph space. So it maps from P1 to you consider maps from P1 to JT stack, for example, and this is just Quasimaps from P1.
Okay.
Yeah, it's nothing. It's more it's definitions. It's you can adjust definitions if you want. So let me just show what I mean by rational tail. So you remember I drew the picture in the very beginning. So we have your compactification M, let's say S, M bar S, and here you allowed in order to compactify. You had to add this rational tails. So rational tails. This is our P1s with the special point. A special point can be either a marking or a node. And so, but in the case of Quasimaps, you remember, we allowed instead of rational tails, we allowed just base points. So we allowed our curve to be fixed, so you didn't have to bubble off. But at the same time, the price that we paid for that is that some points have to map outside of the stable locus. So you have this. Let me draw this. You have this base points. So the base points. Let me actually define what a base point is. So a base point is so it's just by definition, it's a set of points on C that are mapped. So this is P on the points on C that are mapped to unstable locus by the Quasim. And so in particular, it was enough to just add the base points and to make the moduli space compact. So in some sense, you can view you can view this exchange as a kind of an equivalent exchange. So in some sense, this P1s and the base points are in some sense equal. I mean, there are different degenerations in order to make the. I mean, they will equal. They gives to. I mean, I'll talk about in the second talk. The interchange, like exchanging base points for rational tails, is exactly what leads to wall crossing. And so if you add rational tails, you shouldn't allow base points and vice versa, because otherwise there is no point of like adding base points if you added rational tails. So in some sense, rational tails are equal to base points. So it's by equal, I mean it's the degenerate behavior of your moduli spaces in either of these cases. In case of moduli space of stable maps or Quasimaps. So in particular, if you define stability of Quasimap, you shouldn't add rational tails because you have base points. So that's the motivation for this second point here. And it's, I mean, it's essentially the big heart of the Quasimaps. Why that's what makes them different from Gromov-Witten theory. The stable maps is exactly this existence of base points and absence of rational tails. Yes. Yeah, you might. I mean, okay, P1 is a bit is a special situation. So usually, if you study Quasimaps from P1, you require P1 to be fixed. You don't identify maps by automorphisms, and in particular, you can then allow your maps to have infinitely many automorphisms. And so usually when you consider maps from Quasimaps from P1, you consider not stable Quasimaps, you consider just Quasimaps. So that's the point.
So is this like a restriction of the stability condition of mutual ground mobility or an extension?
You mean what with this or
Yeah.
this is a different stability condition? Yeah, it's no. But in the second talk we'll introduce a mixture that will interpolate between Gromov-Witten stability and Quasimap stability. So you're confused about P1?
No. That's fine. I can't really
Okay. Okay, so let me now define the moduli space. So we have moduli space of Quasimaps to our moduli space of sheaves with class beta. So this is by definition is just stable Quasimaps. To V of degree beta genus G with the n markings. Okay, and so I mean in enumerative geometry you can define whatever moduli space you want, but if you want to do some enumerative geometry with it, you have to prove some basic things about your moduli spaces. So here comes now the theorem. So that's justification for why these moduli spaces are reasonable. And so the theorem is that these moduli spaces is a proper for any choice of beta and Gn is a proper Deligne-Malper stack with a perfect abstraction theory. Like bridgeless stability? Yeah, I'll talk about how you prove this theorem. Yeah, so I mean it should be for any bridgeland, for any bridgeland stability or some other sensible stability, not the slope stability, because yeah, I mean the one that has nice good moduli spaces theory. And yeah, so I mean I don't know, I mean there are some technical things here. I mean the theorem is the most difficult part, so this is the technical thing. I mean the point is that we consider maps firstly to stacks that are of infinite dimension, that are of not finite type, and secondly we consider this, these stacks are very singular outside of a stable locus. They're not like they're not locally complete intersections and so on and so forth. And so the fact that it's actually a proper Deligne-Malper stack with the perfect abstraction theory is a bit of a surprise, because I mean it depends on how you view it. But it's not trivial thing because of that properties of our curly MV that I just mentioned. Let me just quickly sketch an idea. Well, if you wanna do. Well, but then you vary the curve, right? As soon as you have. Well, if I can write 0 here with n mark. No, but yeah, it's just. Yeah, I understand you wanted to define those. Yeah. Well, it's important to vary number of markings for the wall crossing formula. It depends of also the genus. Well, in the case of like moduli spaces on symplectic surfaces, probably genus 0 and genus 1 are the only cases. So, but still, already not only genus 0, genus 1 is also kind of important. So I mean, yeah. I could also write, yeah. Yeah, exactly. So usually you just consider a fixed P1 or a fixed elliptic curve, because usually you also study moduli space of sheaves on symplectic surfaces. Well, I mean, del Pezzo is also interesting, but then also, yeah. Yeah, me personally, I haven't done anything but genus 0 and genus 1. But already, because there is genus 1, so I cannot just write genus 0. So, okay, idea, let me just tell you how we prove that. Sorry. I have 2 hours, right? Is it fine if I know? I mean, in total, 2 hours. Okay. Yeah, I can make it as before. Yeah, I think I understand. Yeah, I think it's perfect. So it's you're saying it's fast. Is it a torture or? No. Yes, I'm almost. I mean, there are a few things that I want to say, and it's essentially, I guess that's it for today. I just want to quickly mention how we prove it, and then I'll discuss some examples. Yeah.
So what is the perfect obstruction theory?
It means that it's almost smooth. Yeah, it's quite a smooth. I don't know. So it's perfect abstraction theory. It means that you can. Sorry, perfect abstraction theory means that you have a virtual fundamental class. So it's also called these days, in a modern derived algebraic geometry, it's called quasi-smoothness. So it's smooth in a derived algebraic geometric sense. But so it's almost smooth, let's say. There is another way of thinking about it. So it's smooth up to deformation in some sense. So you can, if you allow, well, it's like in the usual Gromov-Witten theory, a moduli space of stable maps to a symplectic manifold, they are kind of smooth if you allow your complex structure to be almost complex structure that's compatible with the symplectic one. But in algebraic geometry, you don't allow your almost complex structure. You don't allow almost complex structures, you allow only complex structures. So in a sense, this perfect abstraction theory reflects the fact that in symplectic geometry, you can always deform it to a smooth moduli space. So it's like a smooth up to deformation. I don't know, almost smooth. Let's say it's almost smooth. Almost smooth, and so there exists. I mean, why I'm saying that, because in this case there exists a virtual fundamental class, and so you can do enumerative geometry. You can count curves or Quasimaps, or there exists a virtual structure sheaf if someone likes K theory here. Okay. And the idea of the proof, so there are 3 points here. So firstly, it's called the positivity property. Oh, I forgot to actually name people. I mean, let me say. So all these Quasimaps were defined to JT stacks. The JT story goes back to Ciocan-Fontanine Kim Maulik. And so most of the things that I do essentially a way to extend their techniques and their proofs to this the case of the moduli space of sheaves. So all credits goes to them in terms of how you prove properties. So positivity property is where the state that exists. So there exists a line bundle on this huge stack. Such that for all non-constant. I want to also state because I mean, me personally, I don't know how to prove this. Well, for example, for Bridgeland stable objects, I don't know how to prove properness. So I just want to essentially prove a properness and existence of perfect abstraction theory can be kind of boiled down to three technical properties. So the first one is this existence of line bundle, so such that for all non-constant Quasimaps, this Quasimaps, I mean, the pullback of that line bundle is positive. So in the case of a projective variety, this is trivial because your projective variety, you have ample line bundle. So if you map if your map is non-constant to a projective variety, you always pull back a ample line bundle to something positive on your curve. So here the existence of such line bundle is non-trivial property. So this is called positivity property. Then Hartog's property. Hartog's property states the following. So if you take a family of curves or Quasimaps of a disk, such that you defined away from finitely many points, you can always extend it. You can always extend it to the entire family. So this is Hartog's property. So if you have a family of curves over a disk, such that you have a Quasimap defined on that family away from finitely many points, you can always extend it to entire to the entire family, total space of the family. So this is called Hartog's property, and the second one is called I'll call it quasi-smoothness. And this essentially, in this case, quasi-smoothness holds for any even bridgeland stability. Quasi-smoothness. And it's essentially quasi-smoothness. What it states is that you need just MV to be smooth, and the big stack you require to be quasi-smooth. So it has a perfect abstraction theory on its own. And in fact, the perfect, I mean, for the experts, the perfect abstraction theory here is, so you actually study in some sense like a Gromov-Witten theory of a derived stack. So the perfect abstraction theory is given by the pullback of the virtual tangent bundle on this moduli space of sheaves on the surface. So this is, but I mean, for those who don't know abstraction theory, just don't pay attention. So somehow, even though outside of a stable locus, this huge stack is very singular, it's not singular in the right sense, and it's enough to construct a perfect abstraction. So this is the proof, idea of the proof. Yeah, MB is smooth. Yeah. Well, it can be. Actually, I mean, there are cases when I can assume it to be just. I don't assume it's smooth. I mean, I can. You can study Quasimaps to stack as well when you MV is a stack. Huh? Yes. Then it's yeah. Then it's the same as on DT theory on S times C is not defined always, so you have to have some properties. It's exactly the same. In the end, this abstraction theory becomes equivalent to DT abstraction theory on S times C. Say again? Sorry. Say again. Sorry.
So if you apply this result for constant, then
Yeah. Okay. Mm-hmm. Yeah. Good. So let me now say a few words about this moduli spaces. So let me go back. So it's a different chapter, a final one essentially. Quasimaps and sheaves. So remember before we have well, if you take a fixed smooth curve to this curly S, sorry, not the straight S equal. So this the Quasimaps from a smooth curve S, sort of smooth curve C to this stack of Hilbert scheme of endpoints is literally the Hilbert scheme. And now what I want to add is that we have this class beta, and it's going back to Andre's comment. Yeah, so this class beta, essentially beta and V determines Chern character of an ideal sheaf over here. Sorry, beta, in this case, it's V is N. It's in a very precise way, and I guess I don't have time to specify what I mean precisely, but just one-to-one correspondence. Well, at least in if Picard Jacob of S is equal to 0. So this is the first point. Okay, let me now move on. So now we can consider Quasimaps from a fixed curve with a marking. And so what is this in this case? In this case, this is so-called relative Hilbert scheme. I mean, Hilbert scheme relative to the divisor. And the divisor is given by S times P. So what it means is that we consider this accordion of you allow this bubbling in the DT. So this is your S times C, and then this is some S times Q1s, and then you kind of consider this up to some GM action. So this moduli space will be ideal sheaves on these configurations of curves. So sorry, yeah, this is S, this is C, but now C is allowed. C is now at the point P. It's allowed to bubble up rational tails, but it's not rational tails. It's rational bridges because you always have two special points. So this, and then this is S times this picture. Okay. And okay, let's now move on to not Hilbert schemes, but actually like moduli spaces for high rank sheaves. So in case of the moduli space of Quasimaps to high rank sheaf, well, you also have an isomorphism between some moduli space of sheaves, S times C, and so what is this guy? So it's sheaves on S times C, such that the determinant line bundle kind of trivial. I mean, there is a slight technicality, but we can say safely that up to some technicalities, you can assume the determinant of F is just trivial up to some cover, essentially, of a given degree, of a known degree. And then, so the determinant is trivial, and then F not trivial or fixed, and then F is stable with respect to stability of the kind O1 tensored OK, where K is very large. for some given large k, for some given large k, and it will be equivalently stable with respect to all k that are larger than some given large k for which it holds. And then you have a chain character of f is essentially equal to v and then dual over v. And the same with the fixed curve and the marking. So in this case, it gives something interesting because this provides like essentially a moduli space of higher rank sheaves for this kind of geometries for like relative to a point. And so what is the stability in this case? The stability is the following. So you have the same as here. Everything is the same as here. Plus 2 more points. So the first one is that f is stable on the nodes when you restrict the nodes. So when the fiber of f, it should have to be stable when you restrict the nodes on the bubbling of C. And then the second one is that S is stable also on the markings. So you can view it, for those who know, you can view it as a transversality condition in a relative DT theory. Like an extension of transversality condition for relative DT theory. I mean, here also, on nodes, you require that on the nodes and markings, you require that your subscheme is transversal. And in case of ideal sheaves, it's equivalent to being torsion-free and over nodes and markings, and which is also equivalent to being stable in a rank 1 case. In this case, so this is the equivalent. I mean, this is equivalent version of this transversality condition. Okay, so let me just. So in general, let me just. The theorem, in general, if you take this Quasimaps to this V beta, so there are naturally isomorphic to the moduli spaces of sheaves on S times universal curve over MG with cosine. So this is association that sends. So what is this association? You send F to the family big F on S times C, and this moduli space. So this is a. What is this? So this a CGN is a relative. So this is a relative universal curve over MGN. So just universal curve over MGN. And then you have the same conditions. So you have stable with respect to this stability. And you have that stable at the nodes and stable at markings. This is a defining properties of the sheaves over here. And also the curve must be. So this is a semi-stable curve. The moduli space of semi-stable with no rational terms. Okay. So what you I mean, if you don't fully understand what's going on, what you have to take away from from this is that Quasimaps are just literally relative moduli space of sheaves on S times the universal curve over MGN, where you with this properties and with the fact that I mean with a curve required to be very semi-stable. Yeah, exactly. That's how you prove. Exactly. So it's you at least. Yeah, I mean, all of that. So let me go back to this properties. So this comes from theory of sheaves. This comes like from constructions which are classical in some sense in the theory of moduli space of sheaves. this comes from Langton's semi-stable reduction, and this comes from I mean you can construct this positive line bundles. Also, the constructions are known for long. I mean, it's not easy. You have to adjust many things, roughly speaking. Okay. I mean, huh? So let me just go back quickly to your question from the beginning. I mean, the beginning about stable pairs. Okay, and now we'll finish with that. No, I mean it was planned. I was actually planned. So yeah, it was. Yeah, it was planned because it's a quick. I'll finish with that. So it's called perverse Quasimaps. So I mean, what you can do if you want to get a stable pairs, you just fill the moduli space. So you take T to be a dimension of A, and then T that. So now you tilt your category. And then you can define like a tilted moduli space of objects in this category. And for example, so you can define S and tilted. So this is a moduli of objects in this code with a chain character is equal to n. And then you can consider the same pair, but now where the guy is tilted.